should I be
Getting into the,
presentable?
yeah, getting
Or do I
into
have
the
another couple minutes
into the
to
mood. Yeah. Oh,
figure out where on earth I have hidden the slide deck I do want to pull up?
I kind of host quite a lot
You
of
are now
meetings at
live.
work. Oh, hello.
You're live, by the way.
Oh,
Oh, am I
wonderful. Welcome, YouTube audience. Uh,
live on what URL, Nathan?
You what, sorry?
What URL?
I'm about to post away.
Okay.
2 secs.
Good thing I didn't post that on the DAPnet. Okay. Let me just paste it in. We are live.
Wonderful. Okay.
And yeah.
I will get a slide deck up here then, and we'll get rolling.
Excellent. I'm just gonna paste the URLs in all the relevant places. Welcome if anybody's watching on YouTube. We're just getting ready, guys. Just one more here.
Oh, you beat me to it. Okay, cool.
Okay, this will...
Right.
Isn't quite...
I'm making you host again, Vic, because I'm going to drop off.
Okay, I didn't notice you were doing things to me.
I had to take full host to give...
I didn't even notice. Okay, there. I think you have the other profile that you're assigned with is a co-host as well. And do you want this profile that you have a video on to be co-host as well?
Sure. Yeah.
Yeah.
Host
Let's
me
do
up.
that. I will.
Yeah, I will have
I
slides
will.
coming up on this side in just a minute. I think I've now found wanted. Carrying on from 2 weeks ago, the thing that I wanted to find here was kind of an introduction to software-defined radio, starting from the sampling side of things and the signal processing, because that was something that I think hadn't been covered quite as well as we should. But I apologize, work has taken me over, and so I didn't have time to set up. But I know I have all of these slides. They're just slightly less pretty than I would have wished they could have been. Unskip slide, yeah. I have decks and I often skip slides, so there we go. This should work.
Oh, there's one watching now, and I think it's me. I'm my own audience. Excellent.
Okay, wonderful. We've got bits and pieces coming up. So is that correct? We've got 6 people in here, 2 of which are me, 1 is Vic. And so we have 3 live attendees. I guess to start off with, thanks for coming and joining the Zoom call live. And did any of you get a chance to try GNU Radio since last week? Or come up with any questions to stuff that we talked about then? Feel free to unmute or just drop things in chat, which I now have up.
I didn't get to try it because I ran out of space on my computer. That's stupid simple as that over.
That'll do it. Yep, okay. We've got a second person who hasn't tried it. That's fine. And then whoever's watching the recording and stuff, you're on your own. No, catch me in the SDR channel if you do hit any bumps getting it installed or running. Other than that, I think this time we'll run through a little bit more of what is software-defined radio from a theoretical perspective, and I'll be more kind of ad hoc, pulling up different pieces to hopefully kind of make some different points. Live feedback on what's unclear or areas that we should dig into a little bit more is essential. This is a participant sport here. I may be the one up on the field, but we do need supporters here and people calling out topics. So I'll get on with this slide deck, but please throw things into chat whenever you think of them. I'll take on as many as I can, and then we'll go on to probably mostly just playing around a bit with GNU Radio Companion. We had some things that I don't think got caught in the video last time. We'll start there. And hopefully just kind of bring up a bunch of ideas of what's possible. And I'll walk you through just some things that basically I'm working on. And we'll hopefully, I think that'll make a good example. And then if you have things that you're curious about, maybe we can try and build some of those as examples as well.
Derek, I'm just watching YouTube here, so there's 3 watching at the moment. So what I will do is I'll just keep an eye there, and then just interject if there are any questions on the chat over there.
Great, that's perfect. That is perfect. This comes through. Hi, chat. Cool. Grand. Okay, so introduction to radio. So we'll start with this slide deck, and then I'll pull up actually a full schematic, and we'll have a bit of fun digging through that. Because one of the essential takeaways here is that software-defined radio still requires hardware, and many of the problems that people face is a lack of appreciation of just how limited the software-defined part is. Garbage in, garbage out. So your antennas still matter, filters, amplifiers, etc. But we'll get to that. So from the introduction to radio side, I believe this slide deck starts off with some basic pieces of, what are electromagnetic waves. We kind of touched on this a little bit last week, but I'm hoping we can dig into it a little bit better, and specifically some of the sampling pieces. So that was, yes, we're talking about electromagnetic waves. These are a combination of an electric field and a magnetic field, and our antennas are able to both capture some of this energy out of the air and drive some of this energy onto the air. We could get into a whole discussion of different antenna designs and how that works, and pull out some beastly textbooks and stuff like that. But that would definitely be a separate evening. And I think there's entire channels in the open amateur radio, or online amateur radio community Discord for that. So we'll leave that to there. But what do we have? So we've already kind of run through GNU Radio for people joining who didn't see the first half. GNU Radio is a software application and library which you can through programming and through a graphical interface assemble a radio application. But what's it actually doing? It is actually working on batches of samples. And this is something where you have some magical black box that we'll lift the lid of here in a minute, your software-defined radio receiver, which is sitting there attached to the antenna, and it's looking at the voltages and currents coming off of the antenna, and it's just taking a measurement of that. And it's doing that tens of thousands of times a second, up to hundreds of millions of times a second, depending on what type of radio system you're working with. So we've seen this already, where GNU Radio Companion, this graphical application on the left, has a series of functional blocks where the signal is being generated, in this case, sourced out of just a mathematical operation, this signal source, which is generating a cosine wave, into a throttle, because there's no hardware attached in this flow graph yet. So that slows down the processing to run in real time. In this case, 32,000 samples a second, a very common sound card audio rate. And then going out to the Qt GUI time sync, which is what actually generates our graphical user interface. And in this case, basically an oscilloscope time trace. And because these are blue ports on the input and output of these blocks, we are working with a complex sampled signal. And that was what I was hoping to dig into a bit today. And so we get two traces here rather than just one. But they're at the same frequency, and if you combine them together in the way that the radio receivers and transmitters actually work with, you get just a single pure tone out with a single frequency. In this case, 1 kilohertz. So I'm going to skip the automatic code generation. Here is our set of data types, just as a reminder. So the color of the ports changes with what type of data is being moved around. And we're going to dig into why we have the complex and the float here. Our sound card is a great example of something that produces floating point values, and our radios, classically, traditional software-defined radios are pretty much all complex or quadrature sampled signals. So you'll see a lot of the blue. The data, as this slide talks about, comes in, there's really two different ways of looking at the data. There's physically how large is it? Is it 32 bits? Is it 16 bits? Is it an integer? Is it 32 bits? Is it 16 bits? Or is it something like an 8-bit byte? That's the size of the data. Then you have how should you interpret that data? And GNU Radio needs to know both of these. When you say, give me 1,000 samples, or items, as you'll sometimes see it called in the code, it needs to know how much memory to actually grab and manage and move around. So it needs to know what size it is, and then it needs to know what the data actually means. How should it interpret these 32 bits, for instance? And that could be as an integer, it could be as a single floating point number, or it could be as like two 16-bit numbers. So we get all these different combinations. GNU Radio will warn you if you connect the wrong types together, and that can be subtle and confusing, but it won't allow you to generate and run your flow graph application. One of the arrows will turn red, and you can go into the menu and get that list of errors, and I'll definitely throw that up when I have this up. Digital signal processing. So hopefully this is getting, yes. So I think I had this in the first deck, but we'll dig into this a little bit more as well.
Derek, there's a question in the chat.
Yes.
For later on.
For later.
Yep.
Cool.
We can do that, yeah?
Yep. So we have frequency, which is tightly tied into wavelength. You'll see that, well, frequency, number of cycles per second. We do get a little bit of fun when it comes to wavelength. We often speak about amateur radio bands in terms of, the 2-meter band or the 70-centimeter band, go down to 180 meters, where we're talking about wavelength, which is fine and accurate. These are the wavelengths in air. But if you're actually cutting your own antenna, for instance, one of the things that you'll often encounter is that the piece of wire or your piece of coax needs to be a different length than you're expecting. And that's because whatever medium the wave is propagating through has a propagation velocity. And, well, it's never going to be faster than the speed of light. In air, it's pretty close to the speed of light. And then in something like a piece of coax, it can often be as slow as something like 60 to 70% of the speed of light. And so you'll need to cut your piece of coax to a much shorter length than you might otherwise expect. So mostly we think about things in terms of frequency and hope that all of these bits of propagation velocity and stuff like that have been dealt with by the time we're actually doing the sampling operation in a software-defined radio, which turns out to be largely true. Amplitude, how much energy is there in the wave? We can take this, we have the amplitude, and then if you square that, you get power, and that comes very directly from power is P equals V I squared R. So the current squared gives you a square factor. And then phase, which is a bit of a fun one because most of the time you're only looking at a single sine wave. So how can there be an instantaneous phase? But we generate what kind of conceptually is a reference wave. And we say, well, we can look at this wave and say, oh, this is 90 degrees off of some reference. And this is a lot of the problem that you get with a receiver. Hopefully see a little bit more of that later. But yeah, there we go. This is the plot that I really wanted to dig out of this deck. So GNU Radio is going to lie to you continuously and in almost every single plot and present you with a nice smooth line. This is a falsehood, and it's a really important falsehood to keep in the back of your mind, because every operation that GNU Radio and pretty much every form of classical signal processing works upon is that it's working upon a discretely time-sampled signal. You have this array, this long continuous list, and from many perspectives, kind of an unending supply of samples coming out of your radio or sound card or other interface. And the plot on the right is what we actually should be kind of thinking about. There's all of these little there's all these little discrete dots, and anything in the world could be happening between those dots. We don't know what's true there. But GNU Radio is going to make some simplifying assumptions and connect all of the dots, because that's how we're much more used to seeing things. Now, what's the simplifying assumption and why is it valid? You'll hear the phrase Nyquist's theorem or Nyquist sampling rate, and this is because a rather clever chap named Nyquist came up with the basic theory that says, as long as you have two of these points on your sine wave, you can replicate per cycle, so per hertz. You can replicate the original signal without any ambiguity. There's no uncertainty here. As long as you're sampling at least twice as fast as the highest frequency component in the signal that you're sampling. Now, this is often something that people have heard of or will encounter early on in software-defined radio. And the inevitable fun next question is, okay, so I'm trying to sample a signal at 430 megahertz or 440 megahertz. So I need a radio that samples at 880 megahertz, right? You just said I need twice as much as the highest frequency in my signal. And this confounds two pieces. We have our frequency on the air, which has been converted onto some carrier, and then we have our baseband signal, which is the actual information portion of the signal. So if we think of a single sideband signal, for instance, we almost always think of that as kind of 2.5 to 5 kilohertz wide. That's the actual width of our information signal. So if you could get right on top of that signal and just stare right at that one piece of the information signal, you would only have to sample at 10 kilosamples per second to embrace your 5 kilohertz maximum width. This is also why your classical microphone and sound card often work at about either 24 kilosamples per second or 32 kilosamples per second. There's some fun history behind there, but if you divide that by 2, you get down to kind of 15 kilohertz as your maximum frequency, and that matches pretty well with human hearing. There's not a lot of content in music, and certainly not content in human speech, up beyond 15 kilohertz. Now, if you're an audiophile and you've got great speakers and you really want the full experience, and you're young and you've got great ears and haven't been to too many concerts, then hey, yeah, you need more about 20 kilohertz for the maximum frequency our ears can detect. Look up the next sample rate and you get up to 48 kilohertz. You're easily above Nyquist's sampling rate there. Now, there's some error margin there, and any good engineer will tell you don't operate right at the theoretical limit there. So my general rule of thumb is I try and sample 3 to 4 times faster than the sample rate is required. And that starts getting into special cases of, when do you want to go even faster and faster and faster? But as long as you have a bit of a margin, you're going to be able to replicate your input signal quite well. So that's time sampling and a bit about sample rates. Again, throw questions into chat. I have YouTube there, I have Zoom here, and I am seeing things as they come along.
So maybe we can take that question that popped up there. Can you see the chat, Derek?
I can. I see one about LoRa support in GNU Radio.
Yeah.
So I was going to leave that till after the sampling, I think,
Okay, yeah,
because
sure.
it's quite a different level of application.
Okay.
But I will definitely dig into that. I just want to get past the sampling first. So discrete sampling, complex sampling. Cool. So I've just talked about Nyquist sample rate and needing to sample twice as fast as your highest frequency component. My next sentence is, but we get to cheat. It turns out to be really hard and expensive to make fast analog to digital converters and digital to analog converters. There's also a bunch of nuances around why you would want this, but one of the core pieces is that it's just expensive. So as you push to higher and higher instantaneous bandwidths, the bandwidth of your information signal or of the area of the spectrum that you want to monitor, it's really nice to be able to use slower ADCs. And so what can we do? Well, we still need two pieces of information. We're not going to be able to cheat that part. This is a physical limit. But what can we measure? We can measure not only the instantaneous, power, the instantaneous magnitude of a signal at one point, but we can take the signal, split it into two parts, and shift one of them using a sine wave and another one using a cosine wave, and sample both pieces there. And I mentioned this last time. This was Euler's formula, is a way of taking information from a sine wave and a cosine wave and combining them back together to get both amplitude and phase information of a signal instantaneously. So with this, we're able to get two pieces of information at exactly the same time point, squash them back together, and we can replicate that original signal information. That's the whole bottom line. We can now combine two slower analog to digital converters and capture twice as much information as just using one of them, run them both at a slower rate, or capture twice as much spectral data. So the Nyquist's rule gets amended to say that if you're doing real valued sampling, which is what your microphone is doing, for instance, you need to sample twice as fast as your highest frequency component. If you're doing quadrature or complex sampling, then that limit gets divided in half. You only have to sample at your maximum bandwidth. So what does this mean? When you go into SDR++ or a similar application, and you say, well, okay, my RTL SDR can sample at 2.4 megasamples per second. That's quadrature sampling, and you're going to get 2.4 megahertz worth of usable bandwidth out of the radio at that point. So yeah, it's not cheating, but it is a nice fundamental bit. Thanks, Vic, for posting the link to Euler's formula. And that's really the bottom line there. It turns out that you can then apply lots and lots of digital signal processing applications work just as well, or sometimes even better, on a complex on an IQ or quadrature representation as it does on float one. But pretty much all the theory from one applies to the other. So I've already last week shown a couple graphs that had the complex sampling, so I won't pull that up now and slow things down. With the frequency domain, I kind of glossed over this last week, and so I wanted to dwell on this slide a little bit. But we often talk about the Fourier transform or the fast Fourier transform or the FFT size. And I think this becomes a little bit of a magical parameter to a lot of people. And so I wanted to break that down a little bit. What we can look at is that if you have any time domain signal, we are quite familiar as amateur radio operators of thinking, well, there's some information at this one frequency here, and that's basically at some sine wave. And if you retune up a little bit higher, you'll get somebody else. There's information at another signal. I've retuned my radio's oscillator to a different frequency, mixed things down, and I've gotten more information. Well, what would, if you kind of think about it, and then you can narrow your filter and make it narrower and narrower, and you'll get a closer representation of just how much energy is there at one sine wave. If we can imagine having a 1 hertz wide filter. And then we just slowly scan across the band. And if you actually wrote down how much power there was at each point as you were turning your dial, you'd be able to replicate, kind of your instantaneous waveform, how much power there is at different frequencies. This is a little bit of cheating explanation, but it's pretty close to the truth. What we can do is we can take any complicated signal and we can use the discrete Fourier transform to run this experiment mathematically. We take our input waveform, and what this equation actually does, if you dig into it, is it says, okay, for say 1,024 points, we're going to take 1,024 point discrete Fourier transform from our lowest frequency to our highest frequency. We'll create 1,024 test tones at evenly spaced different frequencies, mix our signal with it and do a really really localized narrow filter on it. This is our windowing function. And say how much power fits within this filter and write that value down. And it turns out, because things are fun, if you do this on a complex signal, you also get the phase information. So you'll get the amplitude and phase. If you go back to Euler's formula, that drops out to a full representation of the signal. And that's what the discrete Fourier transform does. It's just sampling the spectrum on an evenly spaced grid. So as we can kind of see on this plot here, we have some slightly complicated signal. It looks like we have like a 2 hertz signal and a 3 hertz signal. So they're they're somewhat, oh no, 2 and 4, like a 2 hertz and a 4 hertz signal. Combining those together, we're getting that nice little notch there. And yeah, I'm not lying there, am I? I should stare at this diagram a little more deeply before I say specific numbers. But we have two harmonically related signals. And we can break those down and see, oh, there's energy at one of these frequencies and there's energy at the second frequency. And that's what the actual frequency display shows us. And then our waveform is that information, or our waterfalls or our pan adapter is that over time. So the frequency sink provides you with all these operations, and you can quite nicely see we have our information about the FFT size. Discrete Fourier transform meet fast Fourier transform. Somebody figured out a really clever way of tying a whole bunch of these operations together. And the nice thing about it is that something like, I should remember the exact math on it, but it changes the complexity of the mathematics quite significantly. A lot of the operations aren't necessary. You get the same math results multiple times if you just do the simple version of the math. Skip all those, and you can do many fewer math operations to get the same end result. It's faster, thus the fast Fourier transform. Now, here's where there's another gotcha with GNU radio. And this was a question that I think came up in the SDR channel quite recently. The center frequency of the spectrum plot is unitless. It doesn't really actually, the discrete Fourier transform doesn't give you any information about your center frequency. It's centered around 0 if you're doing it on a complex signal, or it starts at 0 and goes up to Nyquist divided to your sample rate divided by 2 for a real valued signal. And so you actually need to pass this information to the GNU radio block. So if I tuned my radio to 14 megahertz, I'd have to tell the GNU radio frequency sync block, by the way, we're tuned to 14 megahertz. Whatever you're looking at is centered on 14 megahertz. So there's just a second variable that gets put in there. Certain radios will actually send out information through the GNU radio flow graph and automatically set that. But unfortunately, pretty much none of those are ones that we're likely to be using at home. There's some chance that, depending on where we go with this talk today and this workshop today, I'll actually write one that pulls that information off of my ham radio transceiver, my Kenwood, and puts that along, and we'll see it automatically configured. That would be a fun place to get to. So what does a simple receiver look like? I think I fired one of these up, but we can certainly repeat this a little bit. I was using a little software-defined radio here. This is from Edis Research, but certainly you could use the Pluto SDR, SDR Play, the Hack RF, a whole bunch of these other ones. The RTL SDR is a classical one. All of these just change out this first block for the source block, and GNU Radio ships with blocks for many of those, or they're easily installed, and there's guides on the website for that. Almost all of the common radios are pretty well supported. Now, once you start digging into like the RX-888, you have to dig a little farther to find support, but people have worked on them. We configure what frequency it's tuned to, in this case 100 megahertz, and we configure the receive analog gain. This is 700 milli gain, and it's normalized between 0 and 1. Some radios support an absolute value in dB, and so you can set a gain in dB. And so let me pull up one of those. Now, am I sharing a whole screen? No, I'm not. So I need to stop the share and relaunch it. I will do that. Do I have? I don't. So we'll just go for it. Share the screen. Okay. So this was the waveform demo that we had last week. I'll just create a new flow graph here and pull in. I don't have the radio attached on here. That was part of the problem. I should be able to use a microphone though. So let's try doing that. If not, I know the second computer I have here has both a radio attached and the microphone does work. So an audio source, and we will put that out to a frequency sync and to a time sync, just as a first piece here. So we can see both those arrows are red. We have the wrong type. Our sound card, again, is doing real valued sampling. And so we need to make that match. This alone really kind of should be enough to do this. We save, I hit run, and it starts running, although it doesn't seem like, it helps if I unmute a microphone. And yes, we do get some stuff, grand. So we can see at least a little bit of information being carried out here. This is going through a couple of different pieces, but we can see that as I speak, we are getting some of the waveform information here. And we can see on the bottom, actually, an interesting piece here. So one of the nice things that we get out of complex sampling is twice the bandwidth. This plot very happily shows you one of the fun math properties that if you're doing real valued sampling, the spectrum is symmetrical around the center. And so if I do something nice like whistle, we can see that we get a nice clean tone that's mirrored around 0. That not being particularly useful, we can open up the block again just with a double click, and there's a spectrum width half to reduce that down. And so if I launch that again, we can see just the half spectrum there. So this is a really nice, easy demo that I encourage you to start with, because it's a lot of fun to see your own voice and whistle and be able to see responses. We could chain in things like filters here and quite easily start building up. We could start easily building up a set of blocks. Cool. So we got a question. Are some SDRs better supported than others, or are they all pretty similar? For simple operations, most of the SDRs that you would have likely heard of are fairly equally supported. The ones I listed off certainly all have kind of a roughly equivalent support. The basic ability to set the sample rate, set the center frequency, um, and set the gain are kind of your three basic operations. Past that, you can very quickly get into a lot of nuances where most of the SDRs that sadly people play around with as hobbyists start lacking support for some of the really nice things. For instance, many modern communication systems require a good sense of time. And so the sense of time on your computer is insufficient, really. It turns out that things like FT8 do a lot of tricks to get their timing correct, and they try and pull a lot of information on the receive side to be able to start transmitting at the correct moment. And even then, they kind of jitter around a bit. A lot of work has gone into that particular radio system, that particular waveform mode, in order to be able to transmit using, sound card interfaces and our standard HF radios. If you look up something a little bit more exacting, you get to a place where the timing becomes quite critical. And most cheap software-defined radios don't give you any way of saying, on the next second plus 50 nanoseconds, transmit this set of data. The USRP radio that I'm using has that capability. There is code available for the Pluto SDR to do the same, but it's not the default piece that's available. And moving on from there, you kind of get into more and more expensive pieces of hardware. So the two answers are, there's a lot of nice features in the very expensive radios, but most of the time you don't care about that unless you have a specific need. So if you want to start up your own cell tower, you need a radio that has timing information. If you don't need that, then there's really very little software difference between a cheap RTL SDR and a more expensive thing like a HackRF or Pluto SDR. The best supported one, the support for the RTL SDR is shipped with GNU Radio by default. Most of the other radios require some amount of a plugin. The Pluto SDR has native support as well, so that should be. I'm running a slightly experimental build on Windows here, but there should be. So the USRP is in here. And somewhere else in here would be the RTL SDR block. Beyond that, you pretty much have to install plugins. The Raspberry, so the RSP1B, I'd have to check exactly on the 1B. There was a plugin written. There's a bit of a problem with the SDR Play radios in that their driver can't be open source. And so you have to go to their website to actually download the driver library, and then you pretty much have to compile your own code to connect that to something that GNU Radio can call. It's a fuzzy area, and it limits who is willing to distribute installers for it. I don't know whether the 1B has been updated. I would guess that the old code probably mostly works, and that somebody has certainly written it. I know that the SDR Play folks were really enthusiastic about getting support in, and we just ran into some issues making that happen by default. But I think they were for quite a while distributing an installer and plugins for it. Cool. Yeah. Is it going to start back from? No, it doesn't start back from the beginning. Good. So So I think we saw last week kind of the amplitude modulation, and these are hopefully concepts that are really familiar to people. So there's some AM demo here. I forget whether I linked the slides, but if you go to derekkozel.com/talks, there's a bunch of the slides already up on there, and I can put them into Discord afterwards as well. So here's a nice demo of transmitting narrowband FM. And this is not the way that I would recommend doing it, but it's a nice, straightforward, very direct example that works well. Because what do we have? We have a signal source. This could be your microphone, for instance. In this case, it's just a sawtooth wave. There's no hardware in this because I'm not using a microphone. And so I put a throttle in and I look at the baseband signal. I'll pull up this flow graph here in a moment. Then we put it into a voltage controlled oscillator. This is just a in this, it's just a mathematical function that's taking the amplitude of the input wave and essentially multiplying the amount of phase that it adds per sample. And so if the phase is increasing faster, that's a faster rate of change. Rate of change is frequency. And so you get a higher frequency when the input value is higher. The sensitivity that's there, we can see it's 6.28. If you've been staring at DSP long enough, you're sitting there going, that's 2 pi, isn't it? And that's saying that for every one value amplitude increase, we're going to get 2 pi change per second. And then because this is 628 rather than 6.28, we get 100 hertz change rather than 1 hertz change every second. That might have been a bit of a jump for some folks, but this is a really fun exercise to work through and say, okay, I actually get kind of how frequencies, sampling, and phase connect together as an example. And we'll explore this a little bit when I start running this. I look at that modulated signal on a time sync, and then, okay, we want to zoom in on a spectrum. Well, I've already said a Fourier transform takes a look at an evenly spaced grid of points, and that number of points is based on the amount of data going into it. So if I take that sample rate and I decrease it by 40 times, and I still look at the same number of evenly spaced frequency points, we would get a 40 times zoom on that. And there's some fun bits of math of like refresh rates and how that plays in with it. But by decreasing the sample rate by 40 times, we end up looking at a 40 times more compact grid of frequencies. I shouldn't have thrown FFT size into there. That's incorrect. Is this subsampling? This is decimation, which yes, it's subsampling. It's subsampling or resampling is how I would more often phrase it. We are resampling this to 1/40th of the original sample rate. The other way to kind of think about this is that we have some wide area of spectrum here. Looking at this flow graph, 40 megahertz, 1 megahertz of spectrum, because we have that sample rate variable set to 1 megasample per second. Our VCO is outputting complex, so we do get 1 megahertz of spectrum. And you could think of this as continuous. Think of this as what's on the air, and we're going to then sample it at 1/40th of that rate. So what's that? 25 kilosample per second, 25 kilohertz, rather than 1 megahertz. And all we will get is the information within that one window. Now, the punchline here. This is what happened. This is what it looks like if you don't lose information. We're going to take all of those higher frequency pieces, and if there's energy there, we'll actually fold them back over onto that smaller piece. So let me run this. Let me run this, and I'll re-architect a little bit, and we'll learn what aliasing is and how much of a pain it is. So let me launch that. So that's the FM example. And this is exactly how I'm hoping this works. So throw questions in. I haven't forgotten the LoRa question, and we will get to that. Of course, I browsed away from where I needed to be. Did I open this in a folder? I did. Really plot, narrowband. Well, okay, we'll recreate this. It'll be faster than me fishing around. Of course, it would help if I had this up on the computer with two screens, but hey, we'll bounce back and forth. So we need a signal source. And actually, because I wanted to re-architect this, I'm going to pull out a constant source instead. And this was real valued. I've just used the arrow key while this was selected to change the output type. We needed a throttle because we're not going to attach any hardware to this. Then we needed a VCO complex. And we wanted, what do we want? Let's just go straight for frequency sinks. So that'll be our full rate. So here I will say full base band, 1 megasample per second. This together. And I want a keep 1 in n to do I'll go with the word naive, a naive 40 times decimation. You can see we have keep m and n and some other options. Or the opposite here would be a repeat block. We could repeat the same value for 40 times if we wanted to. And the same thing, another frequency sync. Decimated baseband. We're going to trust my previous self when I said 25 kilosamples per second. Connect that together. And I'm going to get I want to be able to control the input value. GUI range. Constant value. Control value. Default value of 1. Start from 0, and we'll go to, what do we have to go to? I want to go to higher than 1. We're going by 100 hertz for every 1 that we go here. I want to go above 25. We go 500 is probably enough, but 5,000 will be more than enough. What's our constant? Value. So just to repeat the concept there, because this is a critical one, I've just created a Python variable by creating this range widget. The name of the variable is constant value, constant underscore value, and I'm able to control the value that that variable has using the range widget. So I'll be able to actually drag a slider. The value can then be inserted into other functions, into other parameters, just using the name. Anything with an underscore in it in the properties menu can be changed at runtime. So you can change this as the application is running. What do we need? We need a sample rate. That should be populated by default. That's an error. The sensitivity, I wanted to use 3.1415 times 2 times 100. So I want to do 1 full circle is 2 radian, 2 pi. And I wanted to let's get up to a real frequency here. So we'll get a sensitivity of 100 hertz per unit of input value. And amplitude, just a unit of 1. I think that's enough. So let's do this. And I'm going to call this aliasing demo. And hopefully I have understood what I'm doing correctly here. I need the zoom controls to not be on top of my slider. Okay. So what have we got? Our default control value is 1. Our end frequency is 4 kilohertz, which is surprising to me, which means I've probably lost track of something here. But we'll do some experiments and see where that's gotten me to. I'm hoping that if I change this to 2, we'll see that jump up in frequency, and it jumps to 8 kilohertz. So I probably needed to divide it by the sample rate, is the error that I've probably encountered here. And because I have a sample rate of 1 megahertz, it's worked out somewhere. But we can work with this. Work with this very well, actually.
Like the one in N.
Sorry, what was that, Paula?
Did you define the number in the 1 in N division thing?
I think I did set that to 40. We can take a look. Yes, so my N is 40, so I'm discarding 39 samples and keeping 1. So I have slightly misunderstood the sensitivity. It's probably not normalized to sample rate. I need to divide that by sample rate, I would guess. But this actually works out better for my purposes. I will try and correct that here in a minute, just so we can see what that is. I would also go into the documentation to see where that gets us. But as I slowly increase the input value, you can see that for every value, this is jumping us up in frequency by 4 kilohertz, which is not my intent, but works. So what happens when I start creeping this? Do I have one more? I can go up. If I go to 3 point, is this an integer? Do I not get to type in a 5? I apparently don't get to type in a 5. That's disappointing. So what's happened? I've just driven this right up to our upper bounds and of our narrowed bandwidth, so 25 kilosamples per second. We're looking at 25 kilohertz total. When we get up to half of that, 15, 16 kilohertz. 16 kilohertz. Yeah, I can math. Just barely, but sometimes. We see that the signal actually wraps around. So we're seeing it come up as a lower frequency. If we look at the high frequency here, and let me just zoom in so that we can ignore the bottom that we're seeing here with these kind of weird skirts is actually the limit of the processor's ability to represent numbers accurately. But it's, let me zoom out, minus 115 dBm, or dB full scale, minus 110. So functionally speaking, that's the limit of our dynamic range, but that would be more than enough for any real channel. I'll do the same up here. And wow, first hour has flown by. So sorry if people wanted to get to bed early. I'll just keep rolling until somebody throws something at me. But what we're seeing is aliasing. I'll zoom in a bit on the broadband, on the wideband here. So we can see that the real frequency coming out of the voltage controlled oscillator is, oh, that's part of what's, sorry, I've realized what I've done on both of these. So the sample rate, a couple things have happened here, which is what has been driving me a little crazy. I'm glad when there's an explanation. I never changed my sample rate to match what I had on the slide. This should be 1 million or 1E6. That makes this bandwidth make a lot more sense. It's just going to scale everything, but at least it should, I think that should make more of what I was expecting match. And then my comment about you need to set the sample rate. We've just done a decimation here by 40. So I need to divide the sample rate by 40 to get the correct bandwidth here. Sorry, that's unhelpful for explanations, but hopefully these numbers should make a little more sense now. Because I would expect that we can see this just slowly jumping up. Yeah, so we're now seeing it basically probably jump, 10. So an input value of 10 times 100, which was my sensitivity, because I did get the sensitivity correct, gives us a tone at 1 kilohertz. 10 times 100 is 1,000. Thanks for sticking with me, folks. I swear I have done this one a couple times before. So let's jump up in frequency quite a bit. We get up to the end, we get to 10 kilohertz. This also means that I can do what I wanted, which was sneak up on our limit. And our limit, 125, gives us a limit up at 12.5 kilohertz, which is good because that's half of 25 kilosamples per second. All the numbers are adding up. This is the limit of Nyquist for this lower sample rate, and that's the punchline. The punchline is that this decimated rate of 25 kilosamples per second can only accurately tell you information under the assumption that you don't have energy above its sample rate. And because it's centered at 0, that gets divided by half. So 12.5 kilosamples per second from the center frequency is where we run out of our assumption. What does the math do? The math says, well, if it's higher in frequency, there's another answer. It could just be really low in frequency. And I will I'll see if I can turn on some time displays, because that might help. But we see this starts wrapping around. And this is aliasing. So sometimes what you'll end up seeing with a radio is if the anti-aliasing filters aren't good enough, you'll get energy from just above where you're expecting it. If you have a really powerful station sitting just above your passband, you'll see it actually appear at the bottom end of your pan adapter. And that's aliasing. That's what's happening around there. If we had sampled at a higher frequency, we would not be violating Nyquist's rule, Nyquist's assumption, and we'd be able to still accurately represent it, which is what's happening down at the bottom piece here. At the full megasample per second, we have plenty of resolution.
And that bottom piece has moved as well, so because it's very hard to see from the distance that it moved a little bit as well.
Yes. So if I keep ramping this up, we can see that it's slowly rolling because it takes 40 times higher frequency shift to shift over one FFT bin here. Our Fourier transform's sampling grid is 40 times wider on the lower side than it is at the top. Yeah.
That's pretty cool. And if you injected two frequencies, you will see one correct one at the right-hand side, and then the alias will be on the left-hand side, which is represented as a lower frequency, but in fact it's the higher frequency, and then your anti-alias filter will hopefully get fixed.
Yeah. So we could... We'll just keep building this up. This is a nice set of theoretical pieces. So I will harp on it until somebody yells stop. Did not need to grab that. Give me a signal source. So I'm going to pick a frequency here, which is within our sampling band of this lower rate. So our limit was 12 plus and minus 12.5 kilohertz, half of our 25 kilosample per second. So I'll put this up at 10 kilohertz. And I'll put it at a 0.5 amplitude so that we can tell the difference. Hey, well, can't tell the difference very much because I've only reduced it by half, which is 6 dB. So if I zoom in just on the top portion of this, we'll be able to see a little bit better. This tone here is sitting at about -15, -16, and this one is sitting at about -10. So 6 dB, give or take, between the -9.5 and -15. I like it when math works out, especially during a live demo. If I went up to 100, the two powers stack on top of each other, and we actually see some phasing, some fun with the phase. This is actually a bug within GNU Radio partially, and is something that we're working on. Because if we go out here, we can see that the power level is not actually changing. It's an artifact of how the discrete Fourier transform works if you don't do some corrections to it. If we keep marching on, we can see that that frequency wraps around, and on the bottom plot, we can see that these two peaks are just starting to separate, just zoomed in there. And right around here, we should be at about 20 kilohertz, just a little under. And we can see those peaks now separating out.
It's kind of very funny that you're trying to, in digital way, represent the analog signal, and then you hit the analog limitation of your CPU that is causing the that is causing the bottom of it. It's really funny.
Yes. So if we went to, this is a direct, this limitation just below the line I've drawn is because we're using 32-bit floating point numbers. And it really doesn't take that much effort to find a number which cannot fit within those 32 bits, the way they're defined. And so you get this little bit of variation, this little bit of accumulated error away from your perfect sine wave, from the samples that would be perfectly on your sine wave. What do those changes represent as? They represent as high frequency noise. Well, wideband, randomized noise. And so we're essentially looking at additive Gaussian noise here. There's some artifacts in here which we see as spurs based on how the floating point number is actually laid out. We are digging a deep hole here. So to the folks who are watching, thank you for hopefully you enjoy math. Hopefully you enjoy these bits. But yeah, this is aliasing. What's the correct way to do this? I was using the 1 in 40 as a really quick, dirty way of getting this done. What can we do instead? We can, first of all, make this a 2-input frequency sink because I want to look at 2 signals. And we can pull up the rational resampler. Wire that in. And I said we were decimating by 40. So we're not going to change anything about that. So what are we looking at? The blue is our original signal. The red is coming through the rational resampler. There's some tiny, tiny, tiny differences down well into that noise floor. So again, I should just set this up so that it doesn't display this. But basically, there's no difference between the two signals. So what problem have we solved by using the proper block? I shouldn't skip too badly here. So we start seeing, and actually, sorry, I'm going to turn on, there's a control panel here that we can turn on. So if we go under config, we can change we can add on a control panel and take a look at some stuff. We also, while I'm here, can do some nice simple things like say the Y minimum shouldn't be down at -140. Let's focus just at -30, -20. We know that, no, -30, because I do want to show down into that. And we'll do the same thing up here. Again, your patience is really appreciated. Right, okay. So now we have better initial displays and we have a control panel. Why do we have a control panel? Because I want to hit max hold. I'm then going to start moving this across, and we can see that, especially if I give it a moment of time, we get just this tiny little ripple. And this is an artifact of both how we're sampling it and how the Fourier transform works out with certain windows. We get a little bit of what they call scalloping loss as the tone moves between different portions of where it's getting sampled. Basically, if I was moving this exactly in line with those 1024 Fourier transform sampling points, we wouldn't see any change in amplitude. That is a moderately advanced concept, but a fun Easter egg for people who have run into that issue before. Now, what's happening here? A little bit hard to see. So I'll zoom in just on this end point. And the max hold's not going to... Will min hold give me the other portion? No. Apparently, max hold only applies to the first data sample, so we're not getting what I wanted. I'll switch that in a moment. But what do we see? We see that the red line, which is going through the actual, the better resampler block, is starting to fade away right at the edge of our band. What's happening? We're applying a filter. We're applying a low-pass filter. Because what do we want to do? We want to enforce that assumption. And I'll increase the range here so we can keep seeing this. We want to enforce that assumption that Nyquist's sampling theory made, that there's no energy present at more than the permissible bandwidth. So what do? We put a low-pass filter on it and say, hey, we've lost that information outside of our permissible bandwidth. So what's the GNU radio block doing? And if you... Left click doesn't work either. That's annoying. There's no way for me to unzoom here. That's really annoying. This is a bug on Windows with this particular installer. It works with the Radio Conda, but I'm trying to build a better installer. So bug found. I'm just going to quickly swap these two inputs so that we can see that keep max behavior as I was hoping for. So I'm just going to hold this down, scroll it over, and we'll see the filter shape. The GNU radio block of the rational resampler and the fractional resampler will automatically calculate an anti-aliasing filter for you. That's the punchline. Oh, interesting. It gives you the maximum of either of the channels. Of course, we learn. We live and we learn, even when we don't want to. This is probably belaboring a point well beyond what it wanted to be. Crunch, crunch, crunch. But it enforces one of the pieces that software has just as many problems. I'm glad it's still interesting. This should, hey, there we go. There's our filter. And it is true enough that, yeah, it is falling away so fast that I haven't even increased the range enough. This will still, there we go, cool. So if I redo the max hold, we can see that there is still energy that gets aliased, but because of that filter, it's minus 50 dB down from the main tone. There we go. That's the plot I wanted. We can see the anti-aliasing filter actually working. We can see that there is still energy that gets aliased. We haven't cheated the math. We haven't cheated the physics, but we've put in a solution, an engineering answer to the problem. In case you're wondering, this is one of the places where where you get more when you pay more. The RTL SDR has a deeply insufficient anti-aliasing filter. And so when you pay more, you get a better anti-aliasing filter. Now, if you look at something very dedicated, something like the Kenwood TS590S and similar, the new ICOM radios, all the ones that are built around software-defined radio and conventional radios as well, they'll have a really good filter sitting, giving you your narrow band reception. And that is, again, to just eliminate this high frequency energy. So I'm conscious that I've gone an hour and 15. Let's go on to some hardware. Are aliases everywhere in SDR world since you sample? Yes, you are. This is an issue that always crops up, and any real software-defined radio system will incorporate anti-aliasing filters. You hope that the hardware is doing the job, because you can't fix this after the fact. We cannot tell the difference in this top plot between a tone which is here at a low power level being an alias or a real signal, or a true actual signal that just happens to be weak. So that's the punchline, is this has to be fixed in hardware. Now, often you're grabbing this really wide bandwidth, like your full baseband here below, and then on the top side, yeah, you'll compress it down. SDR++, GNU radio, all these other applications, depending on what your end goal is, are going to decimate. At some point, you're going to reduce the sample rate. Why? Because there's no useful information outside of, your single sideband reception or your LTE downlink channel, whatever your signal of interest is. It has a defined bandwidth. We know that there's not stuff we care about outside, and it is computationally expensive to process a bandwidth wider than you need. So you will decimate, and if you're decimating, you will absolutely put an anti-aliasing filter in. Good. I think it would be a really interesting effort at some point for a group of people, not just me, but a group of people, to put together a matching set of SDR content and like signal demos showing in software the key concepts of the different licensing criteria and questions, because I know that there are a bunch of these overlaps. And I think it is a good teaching tool. Right. I think I have probably belabored at this point the piece that says we need hardware. So let's go dig into an actual schematic here for, let's call it 10, 15 minutes or something, and then we'll just go to open questions. I've used it all the time. I'm happy to come back and do this again at some point. So I used to work for Edis Research, so I'm familiar with where all the files are and stuff. This is great. So this was a company founded by an amateur radio operator. It's now very much owned by a very large commercial company. Not that he wasn't running a commercial company, it was a very successful one. But Matt Edis did a really great job in instilling an open source virtue around all of this. So what has good schematics and what has what I want in it? We'll start with this. So what have I just pulled up? Um,
So then, Derek, what we are trying to model in the GNU radio, then we implement in the hardware, so that it's basically faster.
It's a combination of things. Often the goal is to put as little as possible in hardware to keep it as flexible as possible. The trade-off is that at some point you're going to have system requirements. That could be your ability to reject really powerful signals very close to you in frequency. This is quite a common one. It's one we see in RADCOM. It's one we see in every radio review pretty much. And the simple answer there is that there's only so much that you can do in software to solve that problem. The core piece there is that your digitizer, your analog to digital converter, will have a certain performance rating, where if you put in a very powerful tone and a very weak tone, it will give you approximately the right answer, and it will, you'll be able to see it. But if that difference becomes too large, you'll either run out of dynamic range in the digitizer, either digitally, it just doesn't have enough bits to represent a strong signal and a weak signal, or it'll run out of analog range, because even though we call it a digital converter, it is still working at that boundary of analog realm, and it will saturate, it will compress, and it will have problems. And so we can build very great filters on the digital side, but if you want really good close-in rejection, you're going to need an analog filter to remove that power before it saturates your analog to digital converter, or saturates your low noise amplifier, or whatever it is. And so that's the piece that we're at right now. And so you find this balance with certain radios being hardware designed to give you really, really good narrowband signal performance, for instance, or really good rejection of your AM broadcast station that's sitting down the road, or your FM broadcast station that's just saturating you. And RTL SDR will happily pick up copies of all of that mixed in because it's cheap hardware and it doesn't have the filters. You add the filters, you're adding restrictions to the hardware. I don't know if that's a coherent answer to where you were going, but basically every software-defined radio hardware builds in a certain set of limitations, either because it's restricted what you're able to do, and so can give you really good performance in those restrictions, or because it's very general purpose and can't give you really great performance on narrowband signals or on rejecting aliases, something like that. Most of the functionality still gets implemented in software. The radio's job is just to give you as accurate and clean of a copy of what's on the antenna, what's on the air, as possible, good enough that you can then do your software operation on it.
I think
I
I
that's
really,
quite gotten all the way to your point.
I think I had two questions really, but you answered the different questions. But I think what I meant was that you can prepare your graphs and then you can simulate your physical device in the GNU Radio and then build that physical device. That's the one opportunity, because you can happily build, your modulators, demodulators, and stuff like that. And then, but then you understand the theory of the signal at this stage, so you can, you understand what is happening. And the second question is, or was like, yeah, okay, so we need that balance. There is a balance between how much you do in the hardware and then, how much you do in the software, because you have the dynamic range still.
Yes. Okay. Yes. There are some things that you will either need to put in the hardware because you require some physical limitation, or because it's computationally expensive. And then, yes, there's applications where you use of how you use GNU Radio and where do you stick it in. So this is a good place to both stare at this plot and answer the LoRa question, I think. Because the first piece is looking at this plot and saying, okay, what is this radio? And this is actually the flow graph pretty much of the radio that I have, or the schematic, sorry, of this radio that I have here called the B200. So what does it have? It has two antennas, which I have connected here, the receive port and the transmit port. And the transmit port, because it has some switches there, which we can see, can also be used as a receiver. So we have a transmit and receive port, or a receive only port. That goes into a single integrated chip that includes everything that we think of as the analog radio. So this has the local oscillators we can tune to a certain frequency. It has the low noise amplifiers and the power amplifiers. And if I remember that I have a mouse, I can trace this. So let's take the receive path, because that tends to be the easier one to talk about. A signal comes in off of the antenna. It has a low noise amplifier. Often there's multiple ones covering different frequency bands. And then it has a receive local oscillator. In this case, this radio might have 2 receive channels. We mix it down, and there'll be some filtering in here, which isn't shown in this diagram. Gets mixed down, gets amplified again, gets put through an anti-aliasing filter, which is what this block here is showing. And then the analog to digital converter samples that, and it'll sample it at a very fast rate. With this particular chip, depending on how far under the hood you go, it samples it at about 120 million times a second. So we could, and that's complex sampling, so we could look at 120 megahertz of instantaneous bandwidth. That's a lot of data. Like, it's a lot of data. It's gigabytes per second quite easily. So what do we want to do? We want to chop that down to a smaller piece. And we can use the digital down converter here to select a portion of that frequency of our first pass band, our first baseband signal, take a chunk of that, mix it down to 0, and then have anti-aliasing filters that throw away all the data, and then we can decimate it. And that's what's happening inside of this FPGA. An FPGA, a field programmable gate array chip, is programmable logic. It sits halfway between software and hardware. We can change the functionality fairly slowly by programming a whole bunch of logic operations within this. And then it sits as a fixed chip at that point, basically. And that means that it's very flexible. It's very adaptable ahead of time, is what I'm trying to say. You can design exactly what you want this chip to do, and then flash it, and it just keeps doing that one set of operations. We find that things like filters, things like discrete Fourier transforms can be very effectively implemented on FPGAs. In this case, it's doing some filtering, some decimating, and then some control logic and pumping it out over USB 3. And this rate could be anything down to, I think it's about 100 kilosamples per second, all the way up to 61 megahertz of bandwidth. On the transmit side, we have some rate of data coming in that gets interpolated, and we already know very conveniently that there is no energy at higher frequencies. So we can just interpolate up. There's no need for filtering to handle that. The digital up converter can take that piece of spectrum, shift it to where we want it within the passband, send it out a digital to analog converter, which does need a bit of filtering because of the way that those work. You end up with potentially energy at multiples of the frequencies. We want to eliminate that. A power amplifier, still kind of at baseband. And then we mix that with a local oscillator to take that signal from essentially 0 hertz, 0 to 60 megahertz, take that whole band, and we up convert it as a block to some frequency of interest, 2.4 gigahertz or something. Another power amplifier, and then out the transmit side. Questions about this at this point, because what I'll do next is I will pull up a more complicated schematic that basically focuses on everything from the antenna to the edge of the analog to digital converter. So this line right here, focusing on the analog half, because I think that might be of interest to folks. If not, I can skip that.
And that local oscillator and that mixer doesn't have the usual analog mix of all the frequencies. Is it just pushing out that single mix, or is it doing the 2 times frequency, 3 times frequency, and so on?
So it's your classical analog mixer. Most of them are implemented as nice quadrature mixers or like double balanced mixers, and so you'll get very good performance. But yes, you will end up with power at harmonics of the local oscillator and subharmonics of the local oscillator.
Okay, so it's analog mixer. I just thought maybe there's some magic that you can just get the pure product.
No.
No. Okay.
So everything to the right of this line is analog. It's totally conventional analog, just shrunk down to a single chip. Everything to the left of this is digital signal processing on discrete samples. This could be done on your CPU. So this portion, you could exactly, precisely, down to the bit, replicating GNU radio, and that's been done. It's just
Yeah, I
computationally expensive.
just somehow omitted the boundary of the analog digital converter there.
Yeah. This, oh, I was already zoomed in. This is just that analog portion of one of these radios. This is a different board that has a daughter board, actually. Let's go ahead and pull one out, because that's fun and we can. What I have here is the actual software-defined radio. This is a fun radio in that it can receive up to 200 megahertz of bandwidth per channel. So we can do fun things like look at the entire 2.4 gigahertz ISM band quite easily. We're pretty close to the whole band. And how this breaks down inside is that it has two of these daughter boards which implement all of the analog portion of the design. So sitting just underneath these is some traces that go from the analog side, which was what we'll be taking a look at. And this is the exact flow graph for these daughter boards. Underneath this heatsink is the FPGA and a digital to analog converter and an analog to digital converter. And it has enough channels that it can work with two daughter boards. Just for fun, sitting in here while I have this up, you can see a silver box here. This is the actual master frequency reference. This is what do these end up being? 96 megahertz crystal ends up being the main reference. And then sitting right next to it in this particular one is an ovenized reference, which is GPS controlled. So it works very well on the microwave bands. So what does that add up to? Let's chase up from the transmit side. Was that a question, Vic?
No, I was just thinking like the price of this is the square of the frequency it can support.
Yeah, I think the current price tag on that radio as configured is north of 10 grand. So don't drop it. For context, my entire day job in my career is all signal processing, software-defined radio. I helped build and design some of these. Yeah, I work for companies that do this. So it's my day job. That's part of what I get to work with. And I did not pay 10 grand for it. eBay is a wonderful thing. But back to the real point. The real point here is that we have data coming from your digital to analog, your digital to analog converter. We have an I value and a Q value. We have our complex samples coming out, two streams at 100 megasamples per second. That's not right. 200 megasamples per second. This is FC, which is the filter. 200 megasamples per second. These come out. You have some matching networks. You have some anti-aliasing filters coming out, cleaning up those pieces. And one thing that we see is we saw that anti-aliasing filter rolling off the edges of the band, and that happens in this design as well. So while it may send 200 megahertz worth of spectrum, only 160 megahertz of that are clean and level to within a certain degree. What do those do? Those go into mixers. Yay. So we have our IF, our intermediate frequency or our baseband frequency coming up from each of these digital to analog converters, and they're mixed with a local oscillator in a mixer. And we have RF coming out, and you combine those two pieces of RF, and they combine nicely because we generated the signal nicely. And that goes out now as our actual radio's frequency energy here. What's our local oscillator? Our local oscillator is this Maxim chip here, the 2871. This gets programmed to some frequency between, I guess here they're saying you have some low band, which is the 500 megahertz to 6 gigahertz, and then the other bit's going from 10 megahertz to 500. So it gets programmed to some intermediate frequency that you're interested in working with. Goes through some filters to clean it up because even nice synthesizers will still give you tones, and it's nice to just clean it up. This is a Ballon, though it's the other way around. It's an undeballon. Taking your unbalanced signal, turning it into a balanced signal, running that into a phase shifter, giving us a sine wave and a cosine wave coming down, and those go into our mixers. And this is exactly where Euler's formula gets run in the other direction. Sorry, so Vic is asking what is TXI and Q? So these are the two real valued sample streams. Each half of our complex sample is coming in here. So the digital to analog converter sits just to the left of this flow. Everything works better if you put an attenuator in the middle of it. You get better matches and any reflected signal is reduced. So a standard matching trick is to put a bit of an attenuator in. Going through, we have a whole bunch of filters. In this direct path, there's no filter involved. We just pass the signal through, and this is everything 500 to 6 gigahertz. If you want to operate below 500 megahertz, this design, presumably because of some limitation of this mixer or of the synthesizer, or possibly of some bits of filtering, uses some filters and then uses another channel of a synthesizer to lower the frequency of the signal back down to that 0 to 500 megahertz. And you can then have some low pass filters cleaning up everything above that. So Vic, when you were talking about analog mixers, yeah, you'll end up with some higher frequency products when you mix this. Those get removed by this low pass filter. This is a variable attenuator here. So if the signal is too strong, we can weaken it because then there's some fixed gain blocks here that will amplify the signal always. Some of these might be configurable. And then we have our actual SMA connectors out to the transmit side. On the receive side, we have two antenna connectors that can get switched between. Those come through, and we see the same sort of arrangement where different low noise amplifiers will work better at different frequency ranges. It's just one of those nice bits of physics that is really hard to design wideband. So one path will handle between 10 megahertz and 1.5. The other one handles high band, 1.5 to 6. Those get switched through. We have another 6-bit variable attenuator. If the received signal is too loud, we don't want to saturate some of the amplifiers down below, down farther on the receive chain. Direct path for the 500 to 6 gig, and the same thing as we saw on transmit mirrored on the receive path. Everything that's low frequency will be up converted. So if you've ever used, what's it called, the ham it up converter, is just a nice little board you can attach to an RTL SDR or something like that, which will basically add 100 megahertz to whatever you put at the input. So you can shift your HF bands to an SDR that doesn't support HF. Another amplifier, and then we get our quadrature sampling side of things. So we have an analog, real valued, unbalanced signal coming in. That gets run into a Ballon. the signal gets split equally in two sides, and we mix that with a sine wave and a cosine wave. We do anti-aliasing filters. We amplify that a bit more because it turns out that ADCs really want quite a bit of voltage swing to avoid thermal noise, and drive it through another anti-aliasing filter to clean up the output of that amplifier. And just off to the left will be the analog to digital converter. And we have our receive local oscillator here. So that's what a software-defined radio looks like in terms of a whole bunch of hardware. I can post some links to some really fun teardowns of PCBs and stuff like that of some of these. I think the UBX actually has a full yes, he does. It's always daring, I think, to type things into a web browser.
There just a question, the 6-bit attenuator, that's analog attenuator that has 6 bits of range, so to speak. So you can, yeah, okay. So you can set it from 1 to 6,000 or 6 ones, basically.
Yes, 2 to the power 6 bits worth of values that you can configure it to. Usually in something like a half dB step per value.
Yeah.
So that gives you that seems excessive. That seems broader than. I'm always bad. What's 2 to the power 6? No, 64. 64. Okay, so it's a 32 dB dynamic range variable attenuator in half dB steps. That matches what I know the hardware can do. So good. So this is what the circuit board looks like on the inside. These are the underside connectors. So one of these has the lines coming up from the digital to analog converter, and the other side has the analog to digital converter. We'll plug in on these bottom sides, as well as I2C and SPI control lines and the power lines, and actually a frequency reference comes up. I think it's a 100 megahertz clock reference comes up. And we can see a JTAG port for those folks who like hacking on electronics. Another angle of it. Here's our receive and transmit receive SMA connectors. Quite sturdy, actually, thankfully. And the actual top side of the design. So it's always hard to show too much meaning out of this, but it would help if I could remember which one was which. So our left-hand one is, our upper one is the transmit capable side. So that's cool. Sorry, the images aren't even higher resolution. I don't. Hey, much better. Wonderful. Wonderful. Now we're cooking with gas. So here we have a transmit power attenuator coming through with, I should really compare the schematic, but this will be some gain elements. This will be another amplifier, probably, potentially a variable attenuator, but I think it's just a gain element. This is a switch made by Hittite, I believe, from the part number, able to switch between what we saw as the Hittite. This is the switch here. I'm not quite sure what that piece is doing. We have our direct path here, which has nothing affects the signal through here. And then on this side, we have a whole bunch of filters. I should really pull up the other schematic to explain this properly. But it's really fun to look at this. If you haven't, there's a wonderful YouTube channel called The Signal Path, and Shahar does an amazing job of going through teardowns like this. They're almost all RF boards or test and measurement boards. And it's really, really fun to see that. Okay. This is our variable attenuator. This is our 6-bit variable attenuator. That's, yep, 624. That's our part number. So yes, so then yes, we have a gain block and another gain block. This will be a PGA, yeah, PHA +1 mini circuits part number, I think. Don't know what the NB400 is, but yeah, it's a power amplifier, variable attenuator. Coming back, we have our 500 megahertz to 6 gigahertz path. Short, sweet, very clean. On the other side of transmit, we have filters and a local oscillator somewhere in here and a mixer. This will presumably be the mixer. We often see mixers working as balanced circuit elements. I hope that folks watching this enjoy circuits. My career has spanned the software side and the hardware side, and I'm happy to nerd out about either side. Working our way backwards, the path joins up. Somewhere in here, we have our 2 dB attenuator. That's probably this pi arrangement here. Working our way backwards, this is our other mixer, which is generating the I path and the Q path. I don't know which one is I and Q, but this is our I and Q paths here. So these clusters of components here, all of this is our anti-aliasing filter on the transmit side. These will dive down through the circuit board and pump out to that underside connector that we saw before. Somewhere in here, this is our transmit local oscillator, presumably, and our balun going out to feed this. So this probably jumps some connector here, I would guess. I'm not quite sure what that circuit path looks like. On the receive side, we have this switch here, which can switch this port to be a receive port or go from transmit, or we can directly receive. Now, a little fun fact here is you'll actually get a slightly better noise figure if you use the receive only port because you go through one fewer switch. So yeah, how do these paths work? So these are actually microstrip paths, and they are absolutely working as a piece of waveguide, really. You have current flowing in one direction on the top, and it's an RF signal, so it's oscillating back and forth. And then there's a ground plane underneath it, and the electric field is sitting between that top path and the bottom path, and you'll see the current is very tightly controlled, and the electromagnetic field is very tightly controlled between those layers. What you'll see sometimes is paths like this that will have the ground plane very, very close to the outside of the trace, and that's a coplanar waveguide, where the electromagnetic field is actually planar to the trace and working between the edges of the trace and the ground plane rather than from a top layer to a bottom layer. So that's what these traces are doing. And what did we have? We had a switch here, then we have another switch here coming back through. Presumably this is our 500 megahertz to 6 gigahertz path here. Yep. And then on the other side, we have two different LNAs. Sorry, looking at this. So this is the low frequency LNA path because we can see this mini circuits filter. This is a low pass filter here. And a direct path. And this tiny, tiny little chip here is actually the low noise amplifier, just that little silver box. Another switch here. This is the programmable attenuator again. That's the switch. So switch to the programmable attenuator. You can actually see the 6 control bits there, which is good fun. I assume that's the control bits. Coming through, we have our switch. We have our mixer and converter for that low frequency path. So the output of this is actually a higher frequency over here. It's taking our 10 megahertz to 500 megahertz signal and up converting it to, well, I guess above 500 megahertz. I don't know. Is it listing? The IF is 2.4 gigahertz. So it's shifting everything up by 2.2 gigahertz. I realize this is a little rambly. Coming through, filtered, recombined. So this is, at this point, we have some frequency that's above 500 megahertz, which this amplifier probably doesn't work well below 500 megahertz as part of the reasoning. We get amplified, and we come back to our mixer. And so here we have the I and Q portions of our receive path. And we can see even bigger anti-aliasing filters here. And our receive local oscillators. I'll post a link to this so you can run through that. We are coming up at 10 o'clock. Sorry that there's not been as much GNU radio as perhaps anyone expected here, but hopefully we've kind of covered the gamut of why is there hardware in my software-defined radio, and on the other side, what are we actually working with, which is those samples. So turns out there's a whole bunch of work to get from the antenna to those samples that are streaming through GNU radio. There's a whole bunch of examples of the actual code side of things. Please do catch me in the SDR chat if you have questions when you start using it. Does anyone have questions or things they want to chat about here? Sorry, there's the LoRa question to start off with. Having very comprehensively covered the hardware portion of this, let's finally answer the LoRa question. So the question for those watching the video is, how functional is the LoRa support in GNU radio? Could, for instance, I create two simulated LoRa radios and pass data between them? The answer there is that yes, you could. The piece that is not there is the LoRa WAN piece, as far as I know. There's probably somebody who's implemented that. But the actual packet format for LoRa is not implemented in the library that I can think of. So there's some blocks that will turn bits into LoRa symbols, and then LoRa symbols on the receive side back into bits. And so this gives you a very raw view of what's happening with the LoRa signal. The original reverse engineering of LoRa at the physical layer was actually done partially using GNU radio. And so you can go back to probably about 2016, which was a few years ago now. And there's a great video about LoRa at the GNU radio conference, and they show off blocks using GNU radio and being able to transmit and receive LoRa packets with a hardware radio. I think there was some very good LoRa blocks written not that long ago, which may have improved the situation. So there was a talk this last year, 2024, at the GNU Radio Conference on design and implementation of a LoRa physical layer in GNU Radio. So I would chase down that talk. And that covers, the data in, the whitening, the header, and the CRC checksum. So being able to determine whether or not the bits are correct on the other side, encoding, interleaving, mapping, and then finally the modulation, which is where it actually becomes the LoRa physical layer. And so all of those, this actually looks like a really nice presentation. This goes through each of the steps quite comprehensively. I need to watch this talk. But I will. I've just put the slides into the chat on both sides, and there will be a video of that up on YouTube somewhere, presumably with that talk title and the GNU Radio channel. So do definitely hunt that down, because this looks like quite a comprehensive piece, which is nice. And they have a whole set of their blocks. And we really hope that the EPFL, I believe, is quite good at open sourcing things. So hopefully, yes, GR LoRa SDR. All the blocks are there that you should be able to recreate that. I see that Ryan Volts has been in there, so if you use the Radio Conda installer, you should be able to pull up that package. And that indeed includes everything to fully simulate a LoRa radio. Whether or not that's exactly compatible with LoRaWAN, I don't know, or Meshtastic for that matter. But it's certainly more than a starting place there. It probably is enough to get quite far. It includes all the blocks to do that in simulation, and they have examples of using it with a transmit-capable radio. The nice thing is this won't require timing data, so something like a Pluto SDR or a HackRF should get you on the air being able to transmit this. That'd be a fun project. That'd be a fun project.
That'd be pretty cool to do. And I think we have proven in this video beyond any doubt that there is really a real radio there somewhere. Just going through that PCB, right? It's just not bulky and not 24 kilograms, but it's there, you know. So,
and I would even jump on top of that and say, the piece that we see in front of us right now on the screen is at best 1/3 of the hardware of a software-defined radio. You know, this is the low power analog portion. On top of this, you would add your 10-watt power amplifier or your 100-watt or 400. What are we up to these days? Did we get all the way up to 1,500 watts, or it's just a kilowatt? I forget the new Ofcom ruling. But we have a lot more power than we had a year ago.
We've got a no kilowatt.
Oh, excellent. Excellent. So you would add quite a bit more amplification in front of this to saturate us out. And then more filters, honestly. And same thing on the receive side. This has filters, but if I pulled up the plots on them, you'd see that a whole bunch of them are a gigahertz wide. And just simply, you want more isolation than that. You want to protect your analog side as much as possible to get a nice clean signal into the software portion of this. Because at some point you can't recover once things are baked into the signal. You can do quite a lot, but you do hit fundamental problems. Yeah. Any other questions?
Yeah, I'm certainly interested in dragging something out for to assist the learners on the full course I deliver, using GNU Radio to demonstrate various waveforms within analog superheads and things, and also the basic fundamentals of SDR, which is, as far as the full syllabus is quite limited. It's limited as far as Nyquist theorem and alias filters, but that's about it. But certainly for the future, I'm sure that the syllabus will be extended to include more SDR, as nobody manufactures superheads anymore.
Well, the qualifier I would say on that is many people are using superhet designs, but they are doing that final stage into an analog to digital converter rather than your conventional detector.
Yeah, exactly.
So yeah, that'd be really interesting. And if you have diagrams, if you have illustrations that you can describe, I'd be really interested in helping make that happen.
Yeah, thanks, Derek. I've got a course starting in the next couple of weeks, so nothing for that one. But in the break between courses, I'll certainly try and I'll touch base with you and see what we can drive.
Mm-hmm. Great.
Thanks. Or I'll get Vic to do it as well.
yes. Yes, please give me more. Okay, guys, I think that's it. Derek, thank you very much for this presentation. It was really fascinating, and especially, as I say, for me the last part where we actually discovered that there is a radio somewhere in there is really, really, really cool. And lots of cool content can be had from this for the educational purposes, because when you draw these Fourier transforms, these waveforms and stuff like that on the screen, it actually starts to make sense. It's not so abstract anymore to people when they're beginning with the radio, but also to people that never were really interested how it all works. They just have the SSB set and then they go like, hey, but what is actually happening there? So fascinating, and thank you very much for your presentation.
You're very welcome. And yeah, I think that there's a lot of room for using better illustrations and interactive examples to nail these concepts down, because it's not simple. There's very little simple about a modern radio. And the more we can do to let people dig into what's happening to the signal at each and every point along the path, the more people can learn for themselves. That's how it's worked for me, and that's how it's worked for a lot of other people. And it's great to get the tools out there for free. So.
All right, okay. I think we'll have to just disband the Discord for this stream to stop. I'm not sure there's a way of stopping the stream. But also, yeah, just on the off note is that we are trying in the course explain to people how the lower sideband, upper sideband are resolved, and then the moment you have to do this mental flip but also swap because the frequencies are swapping and stuff like that, that is at that stage it can be really overwhelming. So I think with this the software we could probably do it a little bit more intuitive and stuff like that. So thank you, YouTube, for visiting us. I see the 5 people watching. I have no questions there, and I think we'll wrap it up. If there's no more questions, then.
I have a question. If I was to take a real world signal, an audio signal, can I create an INQ from an audio signal? I know you can, if doing it from RF, you can mix it with a sine and a cosine, but can you do the same at baseband? Over.
Yes, you certainly can. And I should know the name of this operation. But it provides you with the analytic signal. And it is called, what is the operation called? The Hilbert transform. There we go. Yes, there is an operation which lets you do this. It is called the Hilbert transform, and it will give you the portion of the signal. It will give you a complex representation of your signal.
Brilliant. Excuse me. Yeah, brilliant. That's I've heard of the Hilbert transform over.
Okay, guys, I'm gonna stop the live stream. Thank you, YouTube, because I found the button now. Good evening, good morning.